Okay, so here's the method of initial rates overview from introduced in lab. The experiment is we measure the initial rate of a reaction, our dependent variable, for a series of experiments with different reactant concentrations, our independent variables. A lot of analogs to any sort of general high school science experiment. We have independent variables, we potentially have controls, and we have our dependent variable. Once we have the rate law of the reaction, now what we're trying to determine is how does the rate depend on the concentration of A and B? What are those orders X and Y? And then eventually at the very end, what's that rate constant K? So remember, the approach we can use is compare trials where only one reactant concentration changes. I've got this mathematical approach here, but you don't usually need to use that approach. The idea is when I compare trials, what I do is I divide the rate law for two trials, and if only one reactant concentration changes, you can see that everything else drops out here. And we just get an equation that looks something like this. That's what our sort of scaffolded steps here look like. We have by what factor the rate changes over here on the left. We have by what factor the concentration changes over here on the right. And then the thing we're trying to find is this order y. We can use logarithms to solve for this, but we'll see that most of the time we can just do this by doing this comparison and seeing, okay, what kind of relationship do I have between my reactant concentration and my rate? Is it rate independent of concentration? Is it linear? Is it squared? Okay. Okay, then the approach that we're going to generally use is this one here, where what we're going to do, again, is make those comparisons, and we can usually see without doing math what's going to happen. Is it rate independent of concentration? Is it a linear relationship? Doubling concentration causes the rate to double. Or is it a squared relationship? Tripling the concentration would cause the rate to increase by a factor of 9. Let's apply that to our problem here, going step by step here. Okay, so here's our problem here. Again, step 1 is the general form of the rate law. That's just rate is equal to K times the concentration of each reactant to a power. So in this case, C₅H₅N to an unknown power X, CH₃I to an unknown power Y. Now we're going to make those comparisons. I think it asks for first, what comparison should we make to determine the rate, the order in C₅H₅N. In that case, we need that to be changed, and we're going to need CH₃I to be constant there. CH₃I is like our control. If we look at what comparison we can make there, CH₃I is constant. We're going to have to compare A to C. This is unchanged as sort of our control variable, and A to C, we can see that C₅H₅N triples going from A to C. So we're going to compare, I would always write like what I put on top first. I'm going to say compare C to A, and then what I'm sort of doing is I'm doing like rate C over rate A is equal to concentration of C over concentration of A to, in this case, the unknown power here is X. So in this case, the factor by which the concentration changed was 3. We tripled the concentration. The rate, okay, this one might be a hard one to figure out by, well, maybe it's not that hard. It just the exponents, you're right. This is 7 times 10 to the negative 7. 6.3 times 10 to the negative 6 is actually 63 times 10 to the negative 7. So 7 times what is 63? That is 7 times 9. This is, in fact, a perfect 9x increase. But again, you're free to just do the division. 6.3 e minus 6 over 7.0 e minus 7. Remember to use that capital E on your calculator so you don't need to add a bunch of extra parentheses. And that would give you 9x is the factor in the rate, 3x is the factor in the concentration. And the equation here breaks down to 9 is equal to 3 to the x. Again, you don't need to write this out if you don't want to. It is, x has to be 2. 3 squared is equal to 9. And again, we can see that we triple the concentration, the rate increases by a factor of 9, which is 3 squared. That's a second order relationship. So second order in C₅H₅N, x is equal to 2 from doing that comparison. Then the next comparison is we're going to need to determine the order in CH₃I. Here, again, I'm going to need to hold the other one constant, hold C₅H₅N constant here. So which trials can we do there? Let's check. A to B looks good. C₅H₅N is constant. And if we look here, this is going to actually be another tripling. So CH₃I triples. What happens to the rate? Well, if I look at the rate, again, we've got exponents going on here, but really if we do everything times 10 to the minus 7, this 2.1 times 10 to the negative 6 is actually 21 times 10 to the negative 7. So 7 times 10 to the negative 7 times 3 is 21 times 10 to the negative 7. Again, if you want it in math, rate B over rate A is equal to, again, 2.1 e minus 6 over 7.0 e minus 7 is equal to 3. So the rate, the CH₃I triples, the rate triples as well. That we should, again, just knowing what we know about relationships here, right? If my independent variable increases by a factor and the dependent variable increases by that same factor, that's a direct or linear relationship. So this is going to be linear, which is first order. Again, we can show the math if you like that, right? Again, if I do, let's say I do the rate factors here in green, the concentration factor here in orange, and I don't know, I'll just use red for my exponent here. The exponent comes up top there, so what this is going to look like is 3 is equal to 3 to the, in this case, the unknown power is y. So 3 is equal to 3 to the y. Again, the only number that makes that equation work is y is equal to 1, right? 3 to the first power is equal to 3. With that, we've finished step 2. The last step here, then, is to determine the rate constant. So in that case here, I can determine the rate constant by plugging into any trial. I'll arbitrarily pick trial A. Now I know that the rate law is not what I had before, but it's now K, C₅H₅N squared. I determined that was a second order relationship, and I determined CH₃I, y was equal to 1, so this is 1 up here. And again, remember, anytime I have a number to the first power, that's just itself. So that's just looks like this. Then I'm going to need to solve for K and plug in. So in this case, divide both sides by C₅H₅N squared, CH₃I. And that will make all of this work out nicely. Now I have K is equal to rate over C₅H₅N squared times CH₃I, which is equal to, again, if I plug in, I'll just arbitrarily pick to plug in trial A. So the rate was 7.0 times 10 to the negative 7, so that goes in there. And then on the bottom, I have C₅H₅N, 2 times 10 to the negative 4. CH₃I, 1 times 10 to the negative 4. Sorry, I'm writing my units wrong here. This is not molar per second, but just normal molar. Okay, then again, we can plug in, solve here. Remember, when you do this on your calculator, you're going to need to do this as like 7e minus 7 over, and then all this stuff is in the denominator, so you need parentheses around it, 2e minus 4 squared times 1e minus 4. And when you do that, you should get your final answer here, which is 175,000. Then the units, right, we just apply that math to the units. If we do that, we have molar per second over, remember that since we have molar squared here, this is going to be molar squared times molar. We can cancel 1 power of molar, and we get 1 over molar squared seconds as the units there.